Homework 3.4, the rational zero theorem, zeros of polynomial functions, video 7. As was stated in the previous video, it was going quite long, and we still have quite a ways to go, so I decided to cut it into 2 videos. In the previous video, we were finding the zeros of this function. We listed all the possible rational zeros. We analyzed Descartes' rule of signs, which told us there's either 2 or 0 positive real zeros, and 2 or 0 negative real zeros. Up to multiplicity, I'll explain what that means in a moment. And instead of just grabbing a number and running with it, we went to Desmos.com and took a look at the graph, which is kind of doing it backwards, because normally what you're doing is finding information to draw the graph, not using the graph to do synthetic division, but it works both ways. And in Desmos.com, we saw a graph of this where the graph swooped down, touched at -1, and went back up, which actually told us 2 things. -1 should be a good box number, because it's an x-intercept, therefore it's a 0 in the function. But because the graph touched and turned, it also told us that this has a multiplicity that's even. So the factor that it comes from has an even power on it, so it's either 2 or it's 4, because it's a 4th degree polynomial. But x plus 1 to the 4th isn't equal to that, I promise you. So I'm pretty confident that when we factor this, not only will x plus 1 be a factor, it'll be a factor twice. So let's run -1 through the box, because that's the x-intercept. It's also the 0 of this factor. All right, I'm just going to go through this. 1, multiply, add to get -3, multiply to get 3, add to get 81. This isn't looking promising. Multiply to get -81. I take that back. Add to get 85, multiply to get -85, and we get 0. Hooray! So what does this tell us? This tells us that we have 2 factors. One comes from the box number. If -1 was the box number, then its factor was x plus 1. Remember, when you go from factor to box, you change the sign and vice versa. But the bottom row represents the other factor. And what power would it start with? Well, this was a 4th degree polynomial, and upon doing synthetic division, the degree gets lowered by 1. So this will be a 3rd degree polynomial. The bottom row represents x to the 3rd power minus 3, x to the 2nd power, plus 81, x to the 1st power, plus 85. So here's the unfortunate twist I alluded to in the previous video. This was a 4th degree polynomial. A good synthetic division problem will take it down to a 3rd degree polynomial. But we don't stop until it's quadratic, because then we can handle it other ways. So what does that mean? That means we have to do all this over again on that. We could make a new list of possible rational zeros, but a quick inspection will show you it's the same list. And now we got to do a synthetic division problem on this guy. So what should we use? In fact, I should have written this to the side, and I'll show you why. F of x equals x plus 1 times x to the 3rd minus 3x squared plus 81x plus 85. The reason I should write it to the side is that if I know I'm about to do another synthetic division problem, I don't need the remainder anymore. I can just pick it up from here. What should I try? Well, technically any number in the list will work, but I already have 1 negative real zero. Descartes' rule of signs says there's 2 or none of them. Well, it's not none, so it must be 2, so there must be another negative number that works. And the fact that -1 was a factor with even multiplicity means that we may be able to use the -1 not once, but twice. So let's try -1 again. It worked before, maybe it'll work again. It will. Bring down the 1, times -1 is -1. Add to get -4, multiply to get 4, it's about to work. Add to get 85, multiply to get -85, and add to get 0. Hooray! So what does that tell us? That tells us that after this first factor of x plus 1, we can now factor this 3rd degree polynomial, because its division's box number was -1, gives us another factor of x plus 1, and the bottom row which now goes from third degree to second degree, is x squared minus 4x plus 85. And at this point, we can cease doing synthetic division because we have other ways of solving quadratic equations. So the zeros, we have x equals -1. Now, did we list it once or twice? Well, it's not wrong if you list it twice. I'm not sure what the homework will specify. Let me see. Type each answer only once. Okay, the reason I wrote it twice was to show you that there were actually two negative zeros. They don't have to be unique, in this case they aren't, and to show you that it showed up twice because it had a multiplicity of 2. That's what multiplicity really means. How many times does the 0 show up? But the homework says only list it once. I am going to write multiplicity 2 down here just because I don't want to just write it once and say it only showed up one time. It's just bothering me. But this guy, we need to break out the quadratic formula. So let's get rid of this graph. Just come up here and do the quadratic formula on x squared minus 4x plus 85. You know what? If you want to use the quadratic formula, go ahead. I'm going to complete the square because it's going to work a lot faster. Remember how completing the square goes. You move the constant to the other side, which is -85. You take half of this and square it. Half of -4 is -2. -2 squared is +4. Add that to both sides. This will factor into the same thing twice. It happens to be x minus 2, because half of -4 is -2. -85 plus 4 is -81, and so we square root both sides. The square root of this is 9i, but don't forget the plus minus. That would get rid of the square here, and then add 2 to both sides. Our other zeros are 2 plus or minus 9i. And this is the result you should get using the quadratic formula. I'm not saying you can't use the quadratic formula. I'm saying that the more proficient you are with multiple methods, the quicker you can do some problems. But the quadratic formula would get you there as well. So, everything came to be as I foresaw. Kind of feel like Palpatine there. We predicted that the rational zeros would be in this list, and they were. We predicted there would be 2 or 0 positive real zeros, and there were none. By the way, complex numbers that are imaginary are neither positive nor negative. It's a little beyond the scope of this course, but you can't define positive or negative. You can't even define greater than or less than when you talk about imaginary numbers. We predicted 2 or 0 negative real zeros, and there were 2 of them. It just happened to be the same one twice. And it's all good. So it takes a while to really internalize the flow of these types of problems. Go find the zeros of these. All right, let me list my possible rational zeros. Maybe I'll look at Descartes' rule of signs. Honestly, you could ignore it and still get the same results. Maybe I'll look at a graph to get a hint on how to start it. Maybe I'll have to do synthetic division more than once because my degree polynomial was too big.